In this video, we're going to take a look at example 28-5. So the first thing we want to calculate is the peak output voltage. But before we can do that, we need to determine what the step-down voltage is. In this example, we've got a 3-to-1 transformer. So our voltage for a secondary is going to equal the number of turns on the secondary divided by the number of turns on the primary times the voltage of the primary. So that's going to give us 1/3 times 120, which gives us 40 volts AC. Since we have a center tap transformer, V1 is equal to V2, which is equal to the secondary voltage divided by 2, and that gives us 40 volts AC. Divided by 2, which is 20 volts AC. Now to find the peak voltage, once again, it's a center tap transformer, so that means V1 peak is equal to V2 peak, and that is going to equal 1.414 times the RMS voltage, the root mean square voltage. And normally whatever's on your print, like this is 120 volts AC, that's going to be an RMS voltage. So we've got 1.414 times our 20 volts AC, and that's going to give us 28.28 volts. Now, because we need to use the second approximation, remember our biasing for a silicon diode is 0.7, our forward bias, so we need to subtract that. So our V out peak is going to equal 28.28 minus 0.7, which gives us 27.58 volts. So that's the answer for part A. Next, we're going to calculate the volts DC, or what we can call the average voltage. And the volts DC is equal to 0.636 times the output peak. So that gives us 0.636 times 27.58, which equals 17.54 volts DC. So it's important to note that we're dealing with three different numbers for voltage. We're dealing with the peak voltage. So number one is the peak voltage. Number two is the RMS voltage, or the root mean square voltage. And then we're also dealing with the average voltage. Okay, so each one of these have a different calculation. So the peak voltage is your max amplitude on your wave. Okay, and you can either use an oscilloscope to determine what that is if you have one, or it's 1.414 times the RMS voltage. And then your RMS voltage, imagine you have your wave here, your sine wave, and your root mean square is going to be somewhere in there will be your RMS, and then your average would be down here if you were looking at, say, the area under the curve. So the root mean square voltage is going to be 0.707 times your peak voltage. And then the average voltage, as we just calculated, is going to be 0.636 times your peak. Okay. Next, we're going to determine what the current is. So we're going to use Ohm's law. So we've got I sub L is equal to your volts DC, or your average voltage, divided by your resistance. We can see that our resistance is 100 ohms. So we have 17.54 volts divided by 100 ohms gives us 175.4 milliamps. Next, we need to calculate the current through the diode. So we just determined that I sub L was 175.4 milliamps. Well, there's two diodes, so each diode is going to get half that current. So the current through the diode is going to equal the total current divided by 2. So that's going to give us 175.4 milliamps divided by 2, which gives us 87.7 milliamps. For part E, we're going to calculate the peak inverse voltage. This is important because that's what your diode's rated for. So if we reverse the current and it's over this number, then our diode is wrecked. So the PIV is equal to the secondary peak minus the 0.7 biasing voltage. So that gives us 1.414 times the 40 volts minus 0.7 volts, which is equal to 55.86 volts. So now for a full wave rectifier, it's going to be the peak voltage of the secondary minus the biasing voltage. Okay. For the last part, we need to figure out what the frequency is, and the output frequency is 2 times the input frequency. So our input frequency was this 60 hertz here. So our F out is going to be 2 times 60 hertz. And that's going to give us 120 hertz.